Hello, this is our first video that discusses material out of sections 10.5 and 10.6 in our calculus text. Our topic for this particular video is going to be the ratio and the root tests. So I want to start off, even though I've asked you to read the section of the text, start off with a statement of the ratio test. So we're given an infinite series. I'm writing it as it's starting at 1, but it's possible it could start at 0 or 2 or some other number. So we're given an infinite series, and we're going to define the Greek letter rho. It looks like a P, but this is a Greek letter rho, to be the limit as n goes to infinity of the absolute value of the ratio of a sub n plus 1 over a sub n. So we're looking at the ratio of successive terms in our series. We're taking the limit of that as n goes to infinity, and assuming that limit exists, we're calling it rho. And so there are three conclusions to be drawn, one of three conclusions to be drawn regarding the ratio test. If rho turns out to be less than 1, so notice that rho is going to be at most, or at least 0, since we're taking a limit of an absolute value of an expression. So we're always greater than or equal to, rho is always greater than or equal to 0. If rho is less than 1, then the series converges absolutely. And I suppose that makes some sense because we're taking an absolute value before we're finding the limit. So we don't have to worry about conditional convergence or anything like that. We're passing straight to absolute convergence there. If rho is bigger than 1, then the series diverges. And then we've got a third conclusion. There's a third possibility, and that is that rho is equal to 1. And it turns out we cannot draw any conclusions at all about the series if rho is equal to 1, because there are infinite series where rho would be equal to 1 that converge and series that diverge. And so literally we cannot decide. It's impossible to know which way it's going to go. There's an example in the text, and I'll remind you of that in just a little bit. There's an example in the text that illustrates this. So let me, in very broad strokes, try to give you a sense of why we should believe the ratio test works, at least in terms of concluding convergence and divergence. So if n is big, then apparently a sub n plus 1 over a sub n, an absolute value, is approximately equal to rho. Now, I'm going to fudge a little bit and just say, let's assume that a sub n and a sub n plus 1 and a sub n are always positive terms. So if we assume that a n is bigger than 0 for all n, we would get that a sub n plus 1 over a sub n is approximately rho, or I could rewrite this as a sub n plus 1 is approximately rho times a sub n. Well, I'm going to unwind a couple more, go a couple more steps here, and then hopefully we'll see what I'm getting at. But a sub n over, let me clean that up a little bit, but a sub n over a sub n minus 1 is also approximately equal to rho. Because I'm taking, again, these are successive terms. N is 1 bigger than n minus 1. So a sub n is approximately equal to rho times a sub n minus 1. And so if I plug that in right here, then this is approximately rho squared times a sub n minus 1. Well, let's do that again. a sub n minus 1 over a sub n minus 2 is also approximately equal to rho. And so a sub n minus 1, again, let me clean this up a little bit. A sub n minus 1 is approximately equal to rho times a sub n minus 2. And we keep on going, and if you'll notice that the sum of these two numbers, n minus 1 and 2, is n plus 1. The sum of n minus 2 and 3 is n plus 1. Eventually we would get down to a sub n plus 1 is approximately equal to rho to the n times a1. So summation a sub n, you want to call it a sub n plus 1 then, is approximately equal to rho to the n times a sub 1. And this right here is a geometric series. So in essence what we're doing is, if a ratio test yields a limit, rho, then what we're claiming in the bigger picture is that summation a sub n roughly acts like a geometric series with ratio rho. And then, but we know the story about geometric series. Geometric series converge when the absolute value of the ratio is less than 1. It diverges when the absolute value of the ratio is bigger than 1. So this is why we are able to, not why, but it gives you at least a bit of believability as to why we're drawing these conclusions from the value of rho in the ratio test. So let me work a couple of examples here. Our first example is summation n equals 0 to infinity minus 1 to the n, 2 to the n over n factorial. An important first step is always to figure out what a sub n plus 1 and a sub n are. Well, since we're taking absolute value, I'm just going to look at this part for our purposes here. So a sub n we're going to take to be 2 to the n over n factorial, and a sub n plus 1 is going to be found by replacing a sub n, replacing n with n plus 1. And so it's going to be 2 to the n plus 1 over n plus 1 factorial. So rho is going to be the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So that's going to be the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. But what I can do is I can rewrite division of fractions as multiplication of fractions. So we get n factorial over 2 to the n here. And one of the big things about the ratio test is it's extremely useful when I look at this ratio of successive terms and I see that there winds up being a lot of cancellation. And that's exactly what we have here, a lot of cancellation. So I can see this by rewriting 2 to the n plus 1, as 2 times 2 to the n, and I can write n plus 1 factorial as n plus 1 times n factorial. So I can quickly see that there are a lot of there's a lot of cancellation here. And so what I'm left with is the limit as n goes to infinity of 2 over n plus 1. And we know that limit, as n gets big, the denominator of that fraction is getting really big. And so I get a limit of 0, which is definitely less than 1. So by the ratio test, summation n equals 0 to infinity minus 1 to the n, 2 to the n over n plus n to the n over n factorial converges absolutely. Let's do one more example, then we'll record another video. Summation n equals 0 to infinity 2n factorial over n factorial squared. It's going to be important for us to get used to this two factorials, and so this will give us a little bit of a good workout with this. So a sub n is 2n factorial over n factorial squared, and a sub n plus 1 is going to be, so we have to be a little bit careful here. I'll do this in a couple of steps. So it's 2 times the quantity n plus 1, all of that factorial, and if I distribute inside there, I get 2n plus 2 factorial over n plus 1 factorial squared. So if I want to find rho as the limit as n goes to infinity, I don't need to worry about absolute value in this particular case because everything is positive. I get a sub n plus 1, and this time I'm going to just rewrite this as a product of fractions this time by inverting the denominator, and so I'll get n factorial squared over 2n factorial. So I'm going to write this out like so, and I'll do it in 2 steps. So I've got n plus 1 factorial times n plus 1 factorial down there, and I've got n factorial times n factorial here. So I'm just rewriting the squares as products of something by itself. And now, here's the key part, and we can talk about this during a class session if we need to, but what I can do to get some cancellation here is I can think about 2n plus 2 factorial as 2n plus 2 times 2n plus 1 times 2n factorial. And likewise, I can rewrite n plus 1 factorial as n plus 1 times n factorial. And so then I've got n factorial over 2n factorial. So please feel free to ask questions if you're not quite sure what I'm doing here. I'm glad to talk with you about this. But now I see oodles and oodles of cancellation. And what I'm left with for the moment is 2n plus 2 times 2n plus 1 over n plus 1 times n plus 1. And I can even do a little bit more here because I see that in the numerator 2n plus 2 factors as 2 times n plus 1. So I can do a little bit more cancellation. And what I finally got here is the limit as n goes to infinity of 4n plus 2 over n plus 1. And we see the degrees of the numerator and denominator are equal. And so the limit's going to be the ratio of the leading coefficients. And so I get 4, which is bigger than 1. So by the ratio test, summation n equals 0 to infinity 2n factorial over n factorial quantity squared diverges.